Good afternoon to everyone. I welcome all of you to the 46th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I'm happy to introduce today's speaker, Dr. Shamik Gupta from TAFR Mumbai. Dr. Shamik Gupta did his PhD in the well-known Presidency College, Kolkata, and post-graduation in the University of Kolkata. He completed his PhD in TAFR under the guidance of Professor Ott-Antonsen, a well-known professor for statistical physics of this country. He carried out his postdoctoral work about 6 years at 3 different places. The first one at the Weizmann Institute of Science, Israel, and the second one at Laboratoire de Physique École Normale Supérieure de Lyon, France, and the third one at Laboratoire de Physique Théorique Models Statistique, University Paris, Sud, France. He spent next couple of years in Italy and Germany as visiting scientist, and came back to India and joined as an assistant professor at Ramakrishna Mission Vivekananda Educational and Research Institute, Kolkata. Last month, he joined back with the TAFR family in Mumbai. Professor Gupta won several awards and honors in recognition of his work. The list is very long. Due to time restriction, I read out only a few. He has been ranked 1, not only in BSc, but also in MSc. He has awarded Alexander von Humboldt Research Foundation for experienced researchers about 2 years back. He has also been recognized as one of the most highly recognized scientists in the early years of their research careers by Institute of Physics, UK. He has organized several conferences. Professor Gupta is working on several topics in nonlinear dynamics. To name a few, I point out he works on stochastic process and stochastic thermodynamics, equilibrium and non-equilibrium dynamics of long-range interacting system, synchronization, and quantum dynamics. Professor Gupta has published a lot of papers in nonlinear dynamics and also written a book named Statistical Physics of Synchronization. Currently, Professor Gupta is supervising a considerable number of students. With this short introduction, now I invite Professor Gupta to deliver his lecture. Over to you, sir.
Thank you very much, Professor Senthilvelan, for the very kind introduction and for the invitation. I have been on and off attending these lectures, and one good thing that pandemic has done is to give all of us an opportunity to sit at home and listen to lectures given by eminent people from around the world. So that is one good thing that has happened. Of course, it strips us of the pleasure of meeting people and visiting other places and so on. But I'm very grateful for the invitation and for giving me this opportunity to talk to you about some work on stochastic resetting. So this is a theme on which I have been working since 2014, and it's been quite a topic of intense research in statistical physics. And recently we used the framework to study some aspects of the Kuramoto model, the well-known nonlinear dynamical system showing synchronization. And this work was done in collaboration with a visiting PhD student, Mrinal Sarkar from IIT Chennai, who is soon moving to Heidelberg for his postdoctoral work. And this paper is to appear in Chaos, and I've given you the archive reference. Okay. So let me start with the general theme of stochastic resetting, and at some point I'll come to the Kuramoto. So here is some real data of stock prices. Okay, so on this side, on the y-axis, you see the stock prices in some units, and on the x-axis, you see the dates. Okay, 87, 7 January 87, 8 January 87, and so on. And what you see from the data is the following: that there are small fluctuations. For example, just one small thing, like, are you able to see my cursor moving?
Yes.
Okay, thank you. So you see that there are some small fluctuations here and there. Okay, for example, this part of the plot shows small fluctuations, but then you see that suddenly there is a huge fall in the stock price. There is a big fluctuation in a very short time. Like, this is 10th of January, this is 11th of January, which means within the span of a few hours, there is a huge change in the stock price. And of course, there are small changes also, as you see here. And this, by the way, came to be known as Black Monday because it led to financial loss incurred by several people in the, like over the, like in different countries. Let me show you another plot. This also has the same generic feature. So this is what is known as Black Plague. So this was this happened in the United Kingdom, and what it shows is that okay, on the y-axis you have the population, the millions of people, and on the x-axis you have year. Okay, this is like 1100 and so on. And again, you see the same generic feature that there are small fluctuations because people die and people are born and so on. But then if there is a catastrophe or if there is a pandemic, the word that we are very familiar nowadays, so then you see that within the span of a few years or months, there is a huge jump in the population size. So these two data hopefully convince you that the basic features of this data are the following. That there is an underlying dynamics. Underlying dynamics meaning, let's say in the case of population, people are born, people die. So there's an underlying dynamics that could be deterministic, that could be stochastic, doesn't matter. But this underlying dynamics is giving rise to small changes over short time intervals. For example, this I would say is a small change over a short time interval. But then there is like there's a different kind of dynamics that is also superimposed on this underlying dynamics, namely that because of something happening in the environment or something that is happening that is causing sudden interruptions. Interruptions meaning that you suddenly see out of the blue there are big changes occurring over short time intervals. So both are occurring over short time intervals, big changes and small changes. Big changes are rare, once in a while they happen, and when they happen, they of course have drastic consequences. While small changes, they are more mundane and regular things. They happen because of the underlying dynamics. So we want to, this is a question that led to this field of stochastic resetting, namely that given such systems where there are small changes and big changes happening together, okay, one is rare, the other one is not so rare. Given such a setup, can one characterize the state of the system at long times? That is, I let this dynamics go on for some time meaning it could be years or months or decade or whatever, and then I wait that long, and then I ask, what is the state of the system like at long times? Like, does the population, let's say for the case of population, you may ask, does the population get completely wiped off? Or what is the steady state size of population after this kind of two competing dynamics go on for quite some time? So, like as a statistical physicist and also as a nonlinear dynamical physicist, as a theoretician more precisely, I mean, our approach is typically to consider a simple setup in which we can at least have some idea as to what would be the state of the system like at long times. And the simplest system that at least comes to the mind of a statistical physicist is that of Brownian motion. So here I have shown a picture of a colloidal particle which is immersed in water. So these black dots, they are supposed to represent the water molecules. And here I have an entity which is a mesoscopic particle. That is, the size of this particle is much larger than the water molecules. But the size of this yellow particle is much smaller than the container size. Okay? And on the right, what I've shown is these are real data taken by the Nobel laureate Jean Perrin, who had studied Brownian motion in experiments. So what he had done was he had monitored the motion of this yellow particle in time, and here I show three trajectories. Okay? So this is why it starts from here, and then it goes once to the left, once to the right, top, bottom, etc. And of course, this is in 2 dimension, but it's always simpler to look at 1 dimension. So this is the position of the particle as a function of time. And what you see is that one remarkable feature of this motion is that even if you start from the same position and you repeat the experiment twice in this case, you don't see the same space-time trajectory. For both these instances, the particle started from position x equal to 4, x is the location of the particle, yet you see that, let's say, at time 5, the particle could be here, location 1 or 6, and so on. And of course, if I repeat the experiments a large number of times, I'm going to see a probability distribution of the position of the particle at a later instant. So we want to play the game of stochastic resetting in this 1D. Of course, we have done work on higher dimensions also, but just for the sake of setting up the stage, let me look at how do I incorporate stochastic resetting in this setup. So what I do is that I take this Brownian particle or diffusing particle in 1D, and this red ones, these are supposed to represent the trajectory of the Brownian particle. Now what I want to do is I want to introduce big changes. As you can see from the red trajectory, this red trajectory has only small changes in small time. Because after all, this particle, it cannot in 1 minute make a jump of 1 centimeter. It will make only small changes, maybe millimeter, even smaller than that. In 1 minute, it cannot just jump to a very different location. So these are the red trajectories. I mean, this sort of motion are represented by the red trajectories. But then what I do is that I want to do resetting. So what I do is that I want to introduce big changes, and the big change that I introduce is the following: that once in a while, that depending on my mood, and I'm a very moody person, so let's say for argument's sake, although I'm not, but let's say I'm a moody person, so once in a while what I do is that I bring the particle from its current location to its initial location. Okay, as you can see here, for example, the particle was here, and then suddenly in no time, instantaneously, I bring the particle from its starting position. You remember x equal to 0, this is the starting position, and I do it several times. How many times do I do? Well, how many times as I wish to do, or let's say how many times as the particle wishes to do. In other words, the time gap between these blue lines, that is the times at which this resetting takes place, these are random variables. For example, this is one particular trajectory of the particle with the resetting and Brownian motion, and this is another trajectory. As you can see, let me just contrast this and that. In both cases, the particle is starting from x equal to 0. In both cases, okay, it is starting from 0. Yet, the times at which it is deciding to reset to its initial location, those times are different. Okay, in this case, these are the times, and in this case, these are the times. The blue, where the blue lines meet the x-axis. So, a technical way of saying this is to say that tau is the time interval between two successive resets. That is a random variable, and this is one realization of the dynamics. This is another realization of the dynamics. And the question is, suppose I play this game. I let the particle do this for a very long time, and then I ask, where is the particle most likely to be found? Okay. What is the probability distribution of the position of the particle? As it is clear from these two plots that at like any given instant, the particle may have many different many different locations. So if you have many different locations, then you can draw a histogram. What is the probability that the particle is here or here or here or here, and this histogram is the distribution, the probability distribution of the particle. And I want to know how does this distribution look like at long times. Before I come to, so why is it called stochastic? It is obvious that stochastic because when the particle decides to reset, that is not a deterministic thing. Out of the blue, sometimes it decides to just go back to its initial location. So that's why it is stochastic. And why it is called a resetting? Because the location of the particle is being reset to its starting location. That is, you start the dynamics anew, afresh. So before I come to what happens to this system at long times, let's just forget about the blue lines and let's just look at the pure normal Brownian motion, diffusion, and let's ask how does the distribution look like. So here there is no resetting. You have a simple Brownian particle, let's say this sort of motion, that you have a particle that is doing Brownian diffusion. You have only small changes in small times, and I wait for a long time, and then what is the probability distribution of the particle? Here I have shown the probability distribution. In case this. Can forget about disregard this notation. This is just the probability of the probability distribution of the particle, namely what is the probability that the particle is at position X at time t, given that it had started from position 0 at time 0. Okay. Simply put, this is just the probability distribution of the particle at time 10, time 20, and time 40. What you see is that first of all, it's a Gaussian distribution with a peak at 0. That means the most likely position of the particle at any instant is 0, which is what you would have guessed, simply because, let me come to it, this particle, it doesn't have any bias in its motion. Sometimes it goes to the left, top, bottom, etc. So therefore, most likely on the average, it would not move anywhere. Displacement, the net displacement will be 0 from its initial location. So that's why you see that there is a peak at x equal to 0, but more than that, what you see is that this probability distribution is broadening as a function of time. So as time goes by, let's say when t equal to 10 to 20 to 40, you see that the probability distribution is broadening. That means, what it means is that there is a significant probability of finding the particle very far away from its initial location. 0 is the initial location, and let's say what is the probability of finding it at location 10 when time is 10? It's very small, but then when time is 20, it increases, and when time is 40, it increases even further. So if I wait long enough, then the particle could be anywhere. The probability distribution is going to be very, very broad, Gaussian distribution. So this is a feature of Brownian motion, and that is simply why is the particle likely, why is the probability distribution broadening? Simply because what I did not tell you is that these data are for a particle which is moving in free space. Okay, if you recall your quantum mechanical problem of a free particle, here also I have a free Brownian particle. There are no boundaries. So the particle can go to any location. Of course, it has to wait longer, and that is why at long times it is able to scan the whole available space. This sort of situation will not happen here for this Jean-Perra's experiment. Here, what is going to happen is that this kind of broadening of the probability distribution will continue until you hit the boundaries. And when you hit the boundaries, then you have equal probability of finding the particle like anywhere within the container. So the main message to take from here is an obvious one, namely that the particle could be anywhere at long times. You have unbounded fluctuations. Fluctuations are typically characterized by the mean square displacement of the particle from its initial location. That is to say, the variance of this Gaussian distribution, and the variance will keep on increasing simply because the distribution just keeps on broadening. So you have unbounded fluctuations in the system. And question is, in this setup, namely pure Brownian motion, what happens when you introduce a reset? So I show you again the resetting protocol that the particle diffuses, and once in a while it comes back to its initial location. And I need to tell you how is the inter-reset time variable distributed. So a simplest situation that you can think of is the distribution is an exponential. Okay, so after an exponential time, exponentially distributed time, it just decides to come back to its initial location. And of course, if you put lambda is a parameter that has to be positive, and if you put lambda equal to 0, you get back bare diffusion. There is no resetting. And since it's an exponential distribution, so you may ask what is the average value of this tau? That you can work out very simply. Tau rho tau integral 0 to infinity, and that will give you this 1 by lambda. That's a time scale. So one thing is for sure that if you keep coming back to its initial location, if the particle keeps coming back to its initial location once in a while, no matter how long you wait, you cannot go very far. Because even if you go very far, there is a finite chance, there is a finite probability that you will come back. So therefore, unlike pure diffusion, where the particle can go, it can start from Mumbai and it can go to Trichy, and then it can go to, I don't know, some city in New Zealand, and maybe in some other galaxy, whatever. But here, what is happening is that I start off from Mumbai and then I travel for some distance and then I keep coming back to Mumbai. Of course, at random times. So therefore, you may expect that even if I play the game for a very long time, there is not much a chance of finding me in another galaxy, because I will come back. The probability will be much smaller. And in fact, that is what happens, that this is the same quantity probability distribution. Let me show you a picture. So this is the same quantity, the probability distribution at long times. So what it does is that it develops an exponential profile. Okay, and this exponential profile, it is time independent. That is, you wait for a long time and you go to a state whose probability distribution doesn't change as a function of time. Unlike here, let me just go back. Here, the probability distribution at long times keeps changing. But here, the probability distribution simply doesn't change. Why? Because you can see that on the right hand side, there is no time dependence. So what it shows is that there is since it's an exponential, it shows that there is a characteristic length scale within which there is a finite probability of finding the particle, and beyond which you have a very small probability of finding the particle. So this is quite remarkable, because what it tells you is that we have been able to bound the particle. That is, the particle simply doesn't go very far from its initial location, but we have been able to do it without putting any boundaries. Because if you had put any boundaries, let's say you had put the particle inside a box, then of course the particle cannot go out of the box. But here the particle is moving in free space. There are no boundaries. Okay, it's a free motion. Yet the motion gets bounded simply because of this resetting business, that the particle once in a while decides to come back to its initial location. And it turns out, I will skip these details, it turns out that this state, this is a stationary state, stationary because the probability distribution doesn't change as a function of time. It turns out that this is the simplest non-equilibrium stationary state. Non-equilibrium in the sense that equilibrium stationary state we encounter in our first and second courses on statistical mechanics, exponential minus beta h, Gibbs-Boltzmann distribution. Here, the distribution is not of that sort. Although it's exponential, but it's not, there is no beta here, there is no temperature, there is no h. You cannot write down a Hamiltonian for the system. So I will skip the details during the question answer session. If somebody is interested, I can come back. Now this stochastic resetting, it was first studied by Martin Evans and Satya Majumdar in 2011, and since then it has found wide applications in many different areas, and this is just to give you a catalog of things that to which stochastic resetting has been applied, let's say like RNA polymerase dynamics, ecology, Ising models, stochastic thermodynamics, quantum dynamics. Again, in quantum dynamics, resetting is similar to what you know, in quantum mechanics, when you do a measurement, you project the state onto the measured state. So a projective measurement in quantum mechanics can be thought of as a resetting. And there is a recent review that one can look. So in this background, I want to ask. Yeah, sure.
Just I have a question. So has this resetting something similar to extreme events?
Yes.
Yeah.
Okay. So that depends on how you choose your distribution. This one. That if you choose your distribution to be such that this resetting happens once in a while, that is, you have to wait for a very long time to have this happen, then you can discuss this in the context of extreme events. Or what you can do is, within resetting, you can ask, although I'm saying that the particle is very unlikely to be found very far from the initial location, still, I mean, the probability is not zero. So you can ask, what is the extreme case in which the particle is, let's say, 5 kilometers from its starting point. But within this framework, I guess you need to play with this distribution.
And how is this resetting done, or who resets?
Okay. So very good question. So what what people have done in the field of stochastic thermodynamics is that there is an external agent. You can think of it like this: that there is an external agent that does the resetting. That is, by force, it brings the particle to its initial location, and in doing so, the external agent does some work on the particle, which gets stored in the particle as its energy. You can think of it that way. The way we deal with, let's say, dynamics in thermodynamics, that somebody is pushing the piston, that is one possibility. The second possibility is there are many natural phenomena where this resetting happens. For example, let's look at like animal ecology. So what happens is that these animals, in the morning, they set out in search of food, but then what happens is that, well, they don't know a priori where will they find food, and so therefore they start doing some kind of random motion. They start looking in this direction, that direction, etc. But once they find food, then there is no point in, of course, they would like to bring back the food to feed their children. And when they come back, they don't need to do random motion because they have found the food. Their objective has been, whatever they wanted to achieve, that has been accomplished. So therefore, you have two types of motion. One is this kind of random motion, but once they are found, they will come straight to their nest or where the children live. And so on that, so there are two changes that are happening. One is this small change and one is this big change. That is one possibility. In computer science, for example, on Google, this is very common. That, let's say, I want to search for something, let's say Mac laptop. So what I do is that I go to Google and I type in Mac laptop, and then it takes me to a page where it's written computer science. I click on it and it takes me to algorithm, and it takes me to algebra, and then mathematics and something. And at some point I realized that no, my actual objective was to look for Mac laptop, and now I have ended up on a page that talks about mathematics and algebra. Probably these two are unrelated. So what you do is that on your browser, you quickly press the back button so that you want to come back to your initial page where you had typed in Mac. So the search process, this is how search processes proceed, that you look for something, and then at some point you realize that you have not been able to find it. So you decide to come back to your initial point and start searching afresh. There are like other examples. For example, this RNA polymerase dynamics. Unfortunately, I won't have time to talk about it. I can talk about it on some like other occasion. There, this resetting is actually what happens, that when these like RNA polymerase synthesizes. So there are two types of motion. One is kind of sliding motion, and the other one can be mapped to resetting. Okay, thank you. Yeah. So the question is, what happens when we play this game with our friend, namely Kuramoto model? So this, of course, I will be very fast. This Kuramoto model is, we all know, it's a paradigmatic model for modeling collective synchronization. And basically what you have is you have a bunch of limit cycle oscillators, and these oscillators are characterized by their phase, which is an angle line between 0 and 2 pi. And the time evolution, the phase, of course, evolves in time, and there are two competing terms in the time evolution. One is the self-sustained oscillation, that is to say, that every oscillator is endowed with its own natural frequency and it tries to move with its own frequency. So I have one oscillator here which moves very fast and one which moves very sluggishly. So that's the first term, self-sustained oscillation. But then there are interactions. So there is an interaction going on between the oscillators that tries to make them phase locked. Okay? So K is the coupling constant, and as you can see, this interaction has such a form that when theta k is equal to theta j, then this term vanishes. D theta dt will be 0 only for this term. And it is a weak interaction because there is a scaling by n. So between any pair of oscillators, the coupling is very weak. And this system, as was shown by Kuramoto, shows a bifurcation from an unsynchronized phase to a synchronized phase. What do I mean by unsynchronized phase? It's a phase in which these red dots, they are supposed to represent the phases, and in the unsynchronized phase, each red dot is going around the circle at its own frequency. Okay? So that is the unsync. There is no synchrony. While in the synchronized phase, what happens is that you find a cluster of these red dots. They would go around the circle with a certain mean frequency. That is to say that the phase difference between two oscillators in the synchronized phase becomes time independent. And to characterize such a system, one defines what is known as an order parameter, R of t. Let me skip the details, just show you that if you take this system, and as you can imagine, when k is 0, that is, there is no coupling between the oscillators, then of course everybody wants to go his or her own way. So then there will not be any synchronization. Every point will be going around with its own frequency. And as you jack up the coupling, then only this interaction term comes into play and it tries to bring together the oscillator phases. So if I take this system, and if I wait for long enough, and of course I have to go to a large number of oscillators because otherwise I won't see a sharp change. I wait for long enough and I look at the stationary value of this quantity R stationary. It's roughly a measure of how, the fraction of oscillators which are phase synchronized. Then what is seen is that when k is 0 or small, then the system is completely unsynchronized. That is, R stationary has the value 0. And as you increase the value of the coupling, the system starts to synchronize. In fact, there is a critical value Kc beyond which the system starts to synchronize, and therefore R stationary starts to increase. And when K is very, very large, then R stationary takes its maximum value 1, meaning that all the oscillators are synchronized. And Kuramoto has shown how to compute this critical coupling in terms of G. What is this G? G is the probability distribution or the histogram of the frequencies. Okay, you have n oscillators, n is quite large, so therefore you can draw a histogram, and G omega is that histogram or probability distribution. So this is for the bare Kuramoto model. And as you can see from this equation, what it suggests is that in a small time dt, theta is going to change by a very small amount. That's why you could write it as a differential. Okay? One thing I should mention, I will mention as we go along, these resetting events, you cannot write them in terms of differential equations because you have a very big unbounded change that is happening in a very small time. In dt time, when you write down these kind of differential equations, then at the back of your mind, you have this understanding that the quantity, the dynamical variable is changing by a very small amount in a small time. But resetting, you see that, wherever it is, let's say I start from Mumbai and then I keep walking or, driving for 10 days. And let's say in 10 days I am in, let's say, Bhutan. I don't know whether it takes 10 days to go there. I'm just making up an example. And then suddenly I reset. So that is, it's going to be a big change in no time. Okay? Now, what happens when I do stochastic resetting? So I should tell you what is the dynamical protocol. So what I do is the following, that I start with an initial condition, namely I tell you the values of the phases of the different oscillators. Okay? And correspondingly, of course, for this initial state, there will be an associated R value. R, remember, R is the order parameter, or it just tells you the fraction of oscillators which are synchronized. Okay, it could be 0, it could be 1, but definitely it's a parameter that lies between 0 and 1. So let me denote it R0. Now what I do is that I evolve following Kuramoto dynamics for a random time tau that I take from a probability distribution, which is an exponential one, and then I reset it to its initial condition. So this picture is showing, is supposed to show it. What I do is that I start with this initial condition. The points are, they are distributed in a particular manner. And then what I do is that I do Kuramoto evolution for a random time tau1, and then I bring it back to its initial condition. And again, I do Kuramoto evolution for another time tau2, bring it back to its initial condition, and so on. And I play this game for a very long time. Of course, this is one realization of the dynamics. In a different realization, this tau1, tau2, tau3, tau4, they are going to have different values. So a different realization would look like this. Okay, so you see that the gaps have changed. The gaps have changed. When do I reset? That is different. And the question that I ask is the same question that I had asked for the Brownian motion. That if I play this game for very long, what is the probability distribution of R? R is going to tell me whether the system is synchronized or not. Is the system really synchronized at very long times? Of course, that will depend on R0, as we will see. But then what is the state like at long times? So the stationary distribution, P stationary R, after I have played the game for a very long time. And once I have the probability distribution, I can find its average. Just for students, I would like to mention one thing, that in the bare Kuramoto model, the order parameter R for a given initial condition has got just one value, because it's a deterministic evolution. But now it's a stochastic evolution. When I do the experiment, although I start from the same initial condition every time, yet at long times I will have many different values of R. So therefore there is going to be a probability distribution, and this is what I have denoted here by P stationary R. So before, okay. So this is, by the way, if I do a simulation of the dynamics, this is R as a function of time. I have started from R0 equal to 1, and then what you see is that, R0 equal to 1, then, R0, depending on k value, it has its own natural evolution, and then once in a while you bring it back to 1. So this kind of behavior resembles sync-fire chains that are used to model neural activity, where you see that you have a bunch of neurons, they at precisely timed intervals, they all fire together. So it's something similar, that they have natural evolution in between, and then once in a while they all become synchronized. That's why R of t is becoming 1. And question is, like, again, I repeat, what is the stationary distribution and what is the average? So let me straight away give you the results, and then depending on time, I'll explain to you how we get it. So this is the phase diagram of the model for a Lorentzian distribution. That is, I take the frequency distribution to be Lorentzian. And now what are the different axes? So this is the k axis. This is the coupling constant k. And what is the y-axis? This is lambda. Let me just come back to the definition. What is lambda? Lambda is, it is characterizing the reset time distribution. That is, 1 by lambda is going to tell you what is the average time between two resets. And of course, if lambda is equal to 0, then there is no reset. Okay? Indeed, when lambda is equal to 0, that is when you are entirely on the x-axis, then you have the usual Kuramoto picture that when k is smaller than kc, the system is unsynchronized. When k is larger than kc, the system is synchronized. But now what I do is that I introduce lambda, I introduce resetting in the system. And what I have shown here is, first of all, let me explain the color code. The color code is the following: that this unshaded region, this is a region in which the system is in the unsynchronized phase. Okay, so unsynchronized phase, which is given by the most probable value of R. Okay, so what is the most probable value of R? This is the distribution as a function of R. The most probable value of R is 0. That is, most likely the system is unsynchronized. If I do an experiment, then I find that in this region, in this unshaded region, the system is unsynchronized, while in the whole of the shaded regions, the most probable value is always non-zero. That is to say that the system is always synchronized in this in these regions, like the pink region and the blue region. And why have I colored them differently? This I have done just to emphasize the fact that the stationary distribution has different analytical properties. Like in some case, it diverges. Like as you can see here, for example, it has a peak here in this region. It has a dip in this region. While in this region also there's a peak and so on. So the stationary distribution, it shows a very rich behavior. But the main take-home message is that if I look at this phase diagram, then the first thing that I see is that in this region, between k and between 0 and kc, when there were no resetting, the system didn't like to synchronize. But when I introduced resetting, provided lambda is larger than some critical value, which is sigma here, that it is lambda has to be larger than this, then you find that the system gets synchronized. So therefore, resetting induces synchrony even in parameter regimes for which the Bayer model doesn't support such a phase. So therefore, resetting has been able to change the nature of the phase diagram in the sense that it is able to induce a synchronized phase even when in the absence of resetting there was no synchrony. You may say that it is obvious that when you introduce synchrony, you are bringing back your system to your initial condition. By the way, my initial condition is R0 not equal to 0. That is, I bring back once in a while to a synchronized state. It could have very low synchronization, but yet you may say that it is obvious that the system will be synchronized. No, it is not obvious, because if it were obvious, I would have seen synchrony even here. I don't see it. I see it only when lambda is larger than a critical value. And here I have shown the average order parameter as a function of k, and it shows a smooth crossover as a function of k. This picture you can disregard.
Professor Gupta.
Yeah.
Sorry to interrupt. So, the difference between this red colored shade and light green colored shade, both the region are resetting is helping for synchronization, right?
Yeah. In both cases, the system is coming back once in a while to synchrony. But you see, if I do a random experiment, that is, I am not going to see. That's why I said that you can disregard the right picture, because here what is giving you is what is the average order parameter if I repeat the experiment an infinite number of times. But typically in laboratory, you don't repeat your experiment an infinite number of times. You repeat it, you don't repeat it, or you repeat it maybe 2-3 times. Now, what is happening is, if you repeat it 2-3 times, then the value of R that you would record in experiment is the most likely value of R by definition, right? Because in experiment, you always capture the most likely value and not the extreme values. What is the difference between the red and the blue is, in this white region, the most likely value of R is 0. That is, the system is unsynchronized. While in this blue and pink region, you see it has vanishing probability when R is equal to 0. That is, if I do an experiment, I am not going to see unsynchronized phase. I am going to see a synchronized phase. Does that answer your question? This averaging you didn't have to do for bare Kuramoto model because your distribution is you have just one R value. So there is no question of averaging. You will get, starting from the same initial condition, you will always get one value at any given time. But here I will get many values, but of course the value that I will measure in experiments or that I will observe in simulations, let's say I don't do simulation runs for 500 times, maybe I do simulation for 10 times, and the most likely value is the value that I will observe by definition, and that value is 0 here and non-zero in these shaded regions.
Okay, good. Thank you.
Thank you for the question. How am I doing with the time?
Yeah, you can go ahead.
Okay. So now I'll give you some flavor of how does one get the analytical results. So first of all, as I mentioned, when you do resetting, this R of t becomes a random variable, in the sense that even if you start from the same initial condition, we are going to get many different values of R at time t greater than 0, unlike the bare Kuramoto model. And so therefore, when you are working in the limit of n going to infinity, why do you need n going to infinity? Well, because if n is 5 or 10, you will get a histogram with a lot of gaps. And I want to define a mathematical function which is very smooth. And therefore, I need to increase the number of oscillators so that I am going to get a large number of values of R. And to characterize it, I define a probability distribution. What is it? It tells you what is the probability of observing R value at time t, given that at time t equal to 0, you started with a given value R0, and then you keep resetting to this value. And of course, this probability distribution, being a probability distribution, is normalized to unit. Now I need to look at how does this probability distribution evolve as a function of time. Why would it evolve? Simply because the thetas are evolving, the thetas are doing resetting and Kuramoto. So when thetas evolve, of course R will evolve because R is defined a posteriori. Given the theta values, I know how to define R. So when thetas are evolving, R will also evolve. And when R evolves, the probability distribution also will evolve. So this is the time evolution equation for the probability distribution. For the moment, we disregard the second and third terms. Let's look at only the first term. What it tells you is that there is probability conservation, because if a certain value of in the Kuramoto dynamics, you have oscillators with a given frequency value, that number, the number of oscillators with a given frequency value, that doesn't change as a function of time. So you have probability conservation under bare evolution. So this is, you may recall, this is what is known as the equation of continuity. We encounter it in electrodynamics, in classical mechanics, in statistical mechanics, Liouville's equation, in several different fields. Whenever there is a conservation, your change of probability can be written down as del P del T is equal to minus del J del theta or del R, okay, where J is the current. So here it turns out that this has this particular form. But now I take into account resetting. And you see, these two things are happening independently. So therefore, the time evolution equation has two parts. One is this part from bare evolution, and this part is coming simply because of resetting. What it tells you is that, let's look at the second term. It tells you that if you are at an R value, then of course, because of resetting, you're going to lose probability. Suppose you are at R equal to 0.28 and let's say you do a resetting. So therefore, the probability to observe that same R value will decrease. So you have minus lambda, but then you will gain at R equal to R0 because you keep resetting to R0. So probability is gained at that R0 value. That's why this term comes with a plus sign, while you lose probability at like other values. Okay. And what I need to do to reproduce or to get the phase diagram is, of course, it's good to note down what are the different parameters. There are so many parameters hanging around. One is the coupling, one is the width of the frequency distribution. The mean of the frequency distribution doesn't matter because it can be scaled out by going to the co-moving frame. The third thing is which value of R0 you are resetting. Okay, and the fourth one is the reset parameter lambda. How often do you reset? How often do you reset? Where do you reset? What is the frequency distribution like? And how interacting are these interacting oscillators? How strongly are they coupled? This is the coupling. So to proceed, I would need DRTT. As you can see, I would need how does the time evolution, how does R change as a function of time? And this, as we all know, this is not an easy task. If I know the distribution of the thetas, to write down a closed form equation for the time evolution of the order parameter is not an easy task unless one considers a Lorentzian distribution where Ott and Antonsen have told us how to look at the time evolution of DRTT. So this is just one very small, very brief primer on Ott-Antonsen ansatz. So what it tells you is that this is for the bare evolution. You remember that this DRTT I need for bare evolution. I don't need resetting to get the form of DRTT. So I'll consider bare evolution. So your bare Kuramoto model, and when n goes to infinity, you define a distribution. What is this distribution? It tells you of the oscillators with frequency like omega and time t, how many of them, what's a fraction of oscillators that have the phase value theta at time t. So what I do is that different oscillators come with different frequencies, so I can think of them as colors. Okay, there are red colored oscillators, blue colored oscillators, green colored oscillators, yellow colored oscillators, and so on. And then what I ask is, suppose I look at the red colored oscillators, they have a particular frequency. I ask at time t, what is the fraction that has the value, that has the phase value theta at time t. And I know how to write down the time evolution equation of this. This will be again a continuity equation simply because the number of red colored balls doesn't change as a function of time. Okay? Because it's a pinch, it's a pinch disorder technical term, but the number of oscillators with a given frequency doesn't change as a function of time. And I know how to write down the order parameter in the n going to infinity limit. It comes out as an integral. That's all fine, and I can also do the following thing, namely that since this f is a periodic function of theta, namely f theta plus 2 pi equal to f theta, because theta is a periodic variable, so Fourier has told us what to do. As soon as you encounter a periodic function, you blindly take the Fourier expansion. So up till now, everything is fine. These steps can be carried out for any frequency distribution. Doesn't have to be Lorentzian. But here comes the genius of Ott-Antonsen. They said that, okay, you see this f tilde n, what is it? This is the Fourier coefficient, like nth Fourier coefficient. And this can have any form. Of course, what form it will take, what I have to do is that I have to take this form and I have to plug it into this equation, and then I have to assume an initial condition to solve this equation. That means I have to assume an initial form for this Fourier coefficient. Ott-Antonsen said that, well, you can come up with 10,000 different initial forms, but suppose you come up with this form where the nth Fourier coefficient is just the z omega t. This is some quantity to the power n. That is, what is the first component? It is, let's say, z. The second component is z square. The third component is z cube. Very, 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 very specific Fourier expansion. Typically, the Fourier series expansion that we do in class or we learn about, they don't have this form. This is a very specific and very special initial condition. And what they showed is that, see, I have this space of many different forms of f tilde, that is to say, many different forms of this f theta omega t. And if I specialize to this very specific form, then I'm going to define a manifold. Okay? I mean, since I'm stipulating, I'm demanding that the Fourier coefficient has to have this form, therefore, in the space of all possible mathematical functions, this is a particular this is a particular manifold. This is my initial condition that satisfies this form. And what Ott-Antonsen says is that it is remarkable that under the Kuramoto evolution, if you start from such a form that lies on the manifold, you continues to remain on this manifold forever. As you can see, this curved line, this just tells you how does the distribution evolve as a function of time following this equation. It doesn't show any tendency to come out of it. And using this, for this particular manifold, they were able to come up with a exact single first order ordinary differential equation for for R of t, namely this form drdt plus f of r equal to 0, where f of r has this form. And from this equation, they find that in the long time limit in the stationary state, r could be 0 or non-zero. R is 0 when k is small, R is non-zero when k is large, and there is a critical point, there is a bifurcation point. This, by the way, matches with the original analysis of Kuramoto. And it turns out that such a thing, this writing down this single differential equation and defining a manifold to which the motion remains confined in time, works out only for Lorentzian distribution. Because I can define a manifold, but if it so happened that during the course of evolution this trajectory leaves the manifold, then there is no point in having the manifold, because I would like my motion to take place on the manifold, but then I can do what is known as a low dimensional reduction of the dynamics, that instead of looking at the big space of all mathematical functions, I'm looking at a smaller space where of course things like become simple. So this is the dividend that we get, that we know how drdt changes as a function of time. So therefore, what I'm going to do is I take my differential equation and I put drdt equal to minus fr. So this is my differential equation. And what I do is that in order to respect this Ott-Antonsen manifold, I will choose my initial state, which is the same as the reset state, to lie on the manifold, because I want to play the game on the Ott-Antonsen manifold. But later on, I will show that the general features of the phase diagram hold even when you don't do Ott-Antonsen, you deal with some other frequency distribution. Of course, you cannot do things analytically, but numerically the same qualitative picture also holds. So this is the differential equation. And now the game is kind of simple, that given this differential equation, I want to go to the long time limit steady state where the distribution doesn't change as a function of time. So the left hand side is 0. So therefore, this is the equation satisfied by the stationary distribution. And of course, I have to like analyze this equation for k larger than kc and k smaller than kc differently, because in one case when k is smaller than kc, then the bare model has a stationary value of r, which is 0, while for k larger than kc, the bare model has a non-zero value. So I have to be careful. A case of triviality is if you put r0 equal to 0, that is, you keep resetting to a completely unsynchronized phase. Then whatever be the value of k, whatever be the value of lambda, your stationary distribution will always be peaked at 0. Namely, you will always be unsynchronized. If you keep coming back to an completely unsynchronized phase, then no matter what happens, and this is kind of trivial, okay? Because if you reset to a completely unsynchronized phase, then of course there is no hope that the system will synchronize. But let us now analyze the situation where you reset to a state which is partially synchronized. R0 doesn't have to be 1, completely synchronized. No. I'm saying that it could be any value, provided it is larger than 0. It turns out that I will skip the details because these are some analytical stuff, but it turns out that you can solve for the stationary distribution analytically, and it turns out that for, let's say, for k smaller than kc, it has many different features. For example, it is monotonically decreasing. It could be non-monotonic with a peak, or depending on the value of lambda is how often you reset. Depending on the value of lambda, it could be monotonically decreasing or non-monotonic, and so on and so forth. I will just gloss over this one, just to mention one thing, that when r goes to 0 plus, that is when you are looking at the value of the probability distribution close to 0. Okay, close to 0. Then it turns out that this has this power law form, epsilon to the power beta. But the interesting thing is that if I have to contrast it with equilibrium statistical mechanics, typically in equilibrium statistical mechanics you have a power law divergence, but usually the critical exponent is a constant. It doesn't change. Let's say if you take a magnetic system and when you are at T equal to Tc, the critical point of magnetization transition, then you see that the magnetization goes to 0, the susceptibility diverges, the specific heat diverges, but the exponent is a constant. It has a given value for a given model, for a given universality class. It doesn't depend on how far or how close you are to the critical point. But here it turns out that this also has this sort of power law dependence, but the exponent beta, it varies continuously with how far you are with respect to this lambda c. What is this lambda c? Lambda c is, if I may go to the phase diagram, lambda c is this line. This line. This line is telling me that when you are below this, your most probable phase is an unsynchronized phase. When you are above this, your most probable phase is a synchronized phase. Similarly, there will be another line lambda star, as you may have guessed, for k larger than kc, and indeed there is one. Yeah, so this is the when lambda, here I have shown the diagram again, when lambda is smaller than lambda c, so you see the most probable value of r is 0. Okay, the peak is at 0. When r lambda is larger than lambda c, then the most probable value is not 0. The most probable value is some non-zero value. That is, if you do an experiment, you are going to see a synchronized phase. This is what I see, and therefore what it has done, and this I'm repeating it, that for k smaller than kc, when the bare model did not allow for any synchronized phase, on introducing resetting, you do get synchrony, provided of course lambda is larger than some critical value that can be computed exactly. The situation is less dramatic when k is larger than kc, then you always have a synchronized phase, excepting that the probability distribution has different forms. You may have a dip, or it could be a monotonically decreasing function, and again there is a lambda star that that kind of demarcates the different behavior of the distribution. But here, whatever be the value of lambda, your probability distribution is peaked at a non-zero value. Let's say here the peak is close to RST, which is non-zero, or here. So therefore the system is surely synchronized when k is greater than kc. Yeah, so this is that when k is larger than kc, sorry.
Professor Gupta, sorry to interrupt.
Yeah, sure.
What is this RD value signifies R of D?
R of D. Yeah. So R of D, it just tells you the location of the dip here. You want to know the physical interpretation or the mathematical?
Yeah, no, I can see that. So there is two situations. Once that initial are not right. So that is
yes. RT is not a parameter. It just comes out of the analysis that your probability distribution will have a dip at RT, provided certain conditions are satisfied. For example, you will have a dip when R0 is less than RT. Then RT has this value. And why do you see this dip? Because you have competing things happening. The system k is larger than kc. The system is trying to synchronize and have the value r stationary, which is r stationary equal to square root of 1 minus kc by k. This is what the bare evolution is trying to do. Bare evolution is trying to go to a value, let's say 0.8. And your resetting is trying to get to a different value of r, namely r0. So let's say on one hand you have 0.8 and on one hand you have 0.6, and as you tune the parameters, I hope you can see my hand. So 0.8 is larger than 0.6, so there will be a point at which it changes. So that's why you see a dip. As you can see, from here to here, it has to pass through a dip.
I understand. Thank you.
Thank you. As I mentioned, this is all very nice, but then you may say that, look, you specialize to a very specific distribution, Lorentzian distribution. Does this picture hold good when you change the distribution, let's say Gaussian distribution? Of course, we cannot do things analytically because there is no Ott-Antonsen ansatz. But, we did numerical simulations and we found that here I have shown only 4 plots, but all the general features that were seen for the Lorentzian distribution also hold when you have a Gaussian distribution. Namely, again, you see that resetting is able to induce synchrony in the system, even when the bare model doesn't allow such a phase. This is the take-home message. You see a very rich phase diagram, all sorts of rich behavior in the stationary distribution. And in the unshaded region, most likely the system is unsynchronized. In the shaded region, colored region, I should say, most likely the system is synchronized. So resetting induces synchrony even in parameter regimes for which the bare model doesn't support such a phase. So perhaps it's about the time to conclude. So I did not have time to bring out the implication as regards non-equilibrium statistical mechanics. But basically what happens is that the stochastic resetting, it leads to new types of stationary states, non-equilibrium stationary states. See, equilibrium stationary states are very boring because whatever system you look at, its equilibrium stationary distribution is e to the minus beta h, where h is the Hamiltonian and beta is the inverse temperature. But for non-equilibrium, it turns out that there is no general framework, so you can come up with a whole sorts of probability distribution. So we found an example of it in the case of Kuramoto. And in fact, over the years, I have been working on this resetting in many different contexts. For example, for diffusing particle at power law distributed times, random walks on random networks, and animal foraging. And recently we did something for quantum dynamics. And then, as I mentioned, that in the case of quantum dynamics, a resetting is like a projective measurement. So you measure and you project the state onto the measured state. Okay, so that is all for now. Thank you for your attention.
Thank you, sir.
Thank you.
So now the session is open for clarifications.
Yeah, Professor Gupta, can you please go to that previous slide? Actually, I missed your that paper 2022. So I'll just take a note. This one.
And just as a reference, when you compare it,
thank you.
Professor Ambika, you want to raise some questions?
Yes, I have one question. Maybe
Yeah, please.
let him finish, then I.
Yeah, you please ask, please. Hello?
Yes. Can I ask?
Yeah, please.
Yes.
Please.
I was wondering whether you have any idea about the probability for the value of R to be 1.
Yes, indeed. That can be.
Zero value doesn't mean it's completely synchronized. Synchronization is when R is equal to 1, no?
Sorry?
So do you have a probability for the value of R to be 1, exactly 1?
Yes. So I'll just come to it. It turns out that when you have resetting, yes, here. You see, when you have resetting, your probability distribution doesn't have a support all the way up to 1. The maximum value that R can take is R stationary, which is a function of Q. Okay. So you have 0 probability of finding the value R equal to 1.
Okay.
Okay, why this is because, so what is happening is that your bare evolution is trying to push it to R stationary. Your say resetting is trying to push to R0, so you will lie in between. Of course, it could be between R0 and R stationary or ulta, the R stationary R0. That depends on what you choose for R0, but it cannot exceed, it cannot go outside this.
Okay. Okay then, thank you.
Thank you.
Shamik, thank you very much for a very beautiful lecture.
Thank you very much.
I have just one question. So you reset always for a particular value or not?
Yes.
So what will happen if you reset in a particular in a small range?
Yes, yes.
Finite number of values.
Yes, indeed, we have done similar things. Not I actually Satya has done this thing that, when you reset, you don't reset to one value, but you choose your value from a distribution. So you say that maybe I will reset to 0.1, but maybe I will reset with a larger probability to 0.8 and so on. I believe at least for the Brownian case, it has been solved, that can be solved analytically. For this Kuramoto case, we haven't looked at it, but certainly it's interesting, and if an opportunity, we plan to look at it. Yes, of course. Then, of course, it will depend on where is the mean of that probability distribution. I mean.
So you expect the results will change?
Results, typically what happens is that qualitatively I don't expect much changes. Of course, these boundaries will move, but qualitatively I have a feeling that it won't change much unless I take a very weird distribution of probability, maybe a bimodal distribution of this sort. Like, let's say you have two values, 0.8 and 0.1, but still I would think that, qualitatively probably it would go to the mean value.
Okay, thanks.
Thank you.
So, is there any other questions or clarifications you need? We are not getting any questions or clarifications. Maybe they will write to you. Okay.
Okay.
Thank you, sir, for accepting.
Thank you very much. Thank you very much for the invitation
and delivering a very interesting lecture.
Thank you very much.
You have shown how Kuramoto model can also be studied in stochastic setting.
Yes, indeed.
I believe the students have some take-home pages.
Yes.
Thank you very much, sir. I will thank you for other details.
Thank you very much. Thanks to the audience and whoever asked questions. Thanks to all of you. Thank you.
Thank you.